We will begin this module by explaining the basic concept of the fly-by-wire system. In conventional aircraft, the movement of the control column is transferred along cables and pulleys until it reaches the control surface to be moved. In the A320 family, the cables and pulleys have been replaced by electrical wires. This has the advantage of saving weight on the aircraft. However, there are even greater advantages, as the video clip will demonstrate. Click on the video window to start it.
Now the way became clear to reassess the mechanical linkages, transferring the control commands to the electrically actuated hydraulic motors that work the flying surfaces. As electrical signals were already being used to control the motors, the logical step now was to send the message to them direct from the control column by electrical wire, resulting in a far simpler and lighter system. And without the need to exert muscle power, the conventional control yokes could be replaced by small side sticks.
The electrical signals created by side-stick movement travel through flight control computers before being passed to the surface hydraulic actuators, also named servo controls. These computers analyze the signal to check that it is a safe command and ensure the optimum flight control surface deflection for the demand. This has advantages over conventional systems. It makes the aircraft extremely stable, enhances safety, reduces the workload of the pilot. Let's now look at the flight control surfaces themselves. The flight control system incorporates ailerons, elevators, a trimmable horizontal stabilizer, THS, for pitch trim, a rudder, ground spoilers, speed brakes. Now let's introduce the ECAM flight control page. You can see that all the flight control surfaces we have talked about are displayed. We will now see them in more detail. The movements of both ailerons and both elevators are symbolized by a green index moving in front of a white scale. The green rudder symbol is used as an index to display the movements of the rudder on a white scale. The rudder trim is indicated by a small blue line below the scale. Note that the rudder and the pedal deflections are limited as a function of speed via a rudder travel limiter. The rudder travel limit is indicated by small white ticks. It is presently in the high speed position. The pitch trim position is indicated by trimmable horizontal stabilizer deflection in degrees up or down. Let's continue with the spoilers. The spoilers have several functions. Speed brakes use the 3 central surfaces. Roll control uses the 4 outer surfaces. On the video, look at the left spoilers as they deploy, then at the right ones as the wings are leveled. Click on the video window to start it. Ground spoilers use all surfaces. On the video, watch as all the spoilers deploy at touchdown. Click on the video window to start it. On the ECAM flight control page, the spoiler extended position is indicated by small arrows. This is the case of the speed brakes. All these control surface indications will be explained in more detail in the normal and abnormal operation modules. Now we will look at the flight control computers. The movements of the flight control surfaces are managed by 7 computers. These are 2 elevator and aileron computers, ELAC, 3 spoiler and elevator computers, SEC, 2 flight augmentation computers, FAC. In addition, 2 flight control data concentrator computers, FCDC, are used to acquire data from the ELAC and SEC. Then they send it to the EIS. However, the data from both FACs is sent directly to the EIS. The status of ELAC and SEC is indicated on the ECAM flight control page. The other computers are not displayed. These indications will be seen in more detail in the abnormal operation module. Now we will see the hydraulic aspect. 3 independent hydraulic systems are used to power all the flight control surfaces. The hydraulic systems which actuate each control surface are indicated on the ECAM flight control page by the use of G, B and Y. For example, the rudder is powered by the green, blue and yellow hydraulic systems. The ECAM flight control page is now complete. Pilots control pitch and roll through 2 side sticks. There are associated side stick priority lights. Side sticks and priority lights will be explained in a separate module. Pitch trim wheels are located on the center pedestal. There are 2 sets of conventional rudder pedals. A rudder trim panel is located on the pedestal. A speed brake lever is located on the left side of the pedestal. In addition, there are 2 panels located on the overhead panel to control the flight control computers. Now we will introduce the lift augmentation devices. There are 5 slats on each leading edge and 2 flaps on each trailing edge. The slats and flaps are hydraulically actuated like all the other surfaces. They are electrically controlled via 2 slat flap control computers, SFCC. Each SFCC has 2 channels, one for the flaps and one for the slats. Each channel can drive its associated surfaces. The flap lever located on the right side of the pedestal operates the slats and flaps. The flap lever has the following positions: 0, 1, 2, 3 and 4. The flaps and slats information is shown on the engine warning display. The flap and slat positions are indicated by white dots. Here the surfaces are extended to position 1 plus F. This is the flap 0 indication. Notice there is no labelling with this setting. The slats and flaps are fitted with protection functions. In particular, surface asymmetry between left and right wing, surface attachment failure, overspeed or uncommanded movement are detected. All these protections will be seen in detail in the abnormal operation modules. In the A320 family, manual roll and pitch are controlled by the side sticks. They are spring-loaded to neutral and receive no feedback from the flight controls. Movement of one side stick will not cause movement of the other. In this case, as the left side stick is moved, the right remains in the neutral position. All side stick commands are processed through the flight control computers before being sent to the control surfaces. You can see that as one side stick is pushed forward, the elevators move down in response. If both side sticks are operated at the same time, their deflections are algebraically added together. In this example, as the side sticks are moved in opposite directions, the elevators remain in the neutral position. When both side sticks are moved in the same way, the total demand is never more than full deflection on only one side stick. Here, as both side sticks are moved forward, the elevators achieve normal full down deflection, but no more. When either autopilot is engaged, both side sticks lock into their neutral position. Notice that if a pilot applies sufficient force, the side sticks become free, and the autopilot disengages with audio and visual warnings. Move the left side stick. The autopilot has disengaged. The associated audio and visual warnings will continue until cancelled by the crew. As you will perform this many times in your simulator sessions, we will now continue with the autopilot disconnect and takeover push button. The autopilot has been re-engaged for you. Each side stick is fitted with a red autopilot disconnect and side stick takeover push button. By pressing it, a pilot disconnects the autopilot. Disconnect the autopilot. Notice on the FCU that the autopilot has disconnected. The associated audio and visual warnings can be cancelled by pressing the autopilot disconnect push button a second time, or will stop automatically after a few seconds. A side stick priority logic is also available. Let's study it in more detail. By pressing and holding a takeover push button, a pilot can deactivate the opposite side stick. Audio and visual indications are provided to identify which pilot has control of the aircraft. You are sitting on the left. Take priority.
Priority left.
You heard the audio warning. Notice there is also a red side stick priority arrow in front of the first officer, indicating that his side stick is inoperative. The arrow points left, showing that the captain has control. If the first officer had taken over, the message would have been priority right, and the red arrow in front of the captain would have illuminated. To see what happens when the deactivated side stick is moved, move the first officer side stick. A green light illuminates in front of the pilot who is in control of the aircraft. Here, the captain. As soon as the deactivated side stick is returned to neutral, the green light extinguishes. If both pilots press their takeover push button, the last one gets the priority. If it is necessary to deactivate the opposite side stick permanently, press and hold the takeover push button for at least 40 seconds. To reactivate a permanently deactivated side stick, either pilot has to press his takeover push button momentarily. Notice that both side stick priority lights are extinguished.
Dual input.
You heard the audio warning and saw both green side stick priority lights flash, indicating a simultaneous control input. Simultaneous control inputs are never recommended. If the pilot non-flying must make a control input, he must press his takeover push button. We will now study the normal law module. In this module, we will be looking at how an A320 pilot and the aircraft computers interface to ensure safe and accurate flight with minimum workload for the crew. For clarity in this module, most references will be made to manual flight inputs. However, the references apply equally to automatic flight unless stated otherwise. A side stick, or an autopilot, sends a message to the flight control computers, demanding an aircraft maneuver. The flight control computers process the demand and send it to the control surfaces. The processing uses preset limitations and instructions called laws. The aircraft responds conventionally to the movement of control surfaces. Normal law is modified depending on the phase of flight. It operates in 3 modes. Ground mode operates on the ground when the aircraft is electrically and hydraulically powered. Controls are conventional. Flight mode operates in the air after a gradual transition from ground mode just after liftoff. This will be discussed in detail as this module continues. Flare mode modifies the flight mode to introduce a conventional feel to the landing phase. This will be discussed later in this module. We will compare a conventional aircraft, an A310, with the fly-by-wire A320 in normal law flight mode. Control surface deflection is directly proportional to control yoke deflection. The same yoke input produces a higher rate of pitch roll at high speed, lower rate of pitch roll at low speed. Control surface deflection is not directly proportional to side stick deflection. A side stick deflection gives a rate demand to the flight control computers. The flight control computers set control surface deflection to meet the rate demand. For the same side stick input, the control surface deflections will be large at low speed, small at high speed. A side stick input is a rate of roll demand in roll, load factor G demand in pitch. Yaw control is conventional. Remember, the A320 responds conventionally to the movement of control surfaces. However, unconventionally, the response information is fed back to the flight control computers. The computers process this feedback and adjust control surface deflection to ensure that the maneuver rate demand is executed accurately. This means that control surface deflections may be altered with no change in side stick position. In flight mode, if you wish to execute, for example, a descending left turn, you set the required attitude and then return the side stick to neutral. The neutral side stick position demands 0 rates of pitch and roll. The flight control computers will maintain the set attitude until you use the side stick to demand an attitude change. Throughout the maneuver, there are no pilot trim inputs. Turn coordination and Dutch roll damping are automatically provided in normal law. Pilot inputs on the rudder pedals are not required. Normal law provides a number of airborne pitch protections. They are load factor limitation, pitch attitude protection, high angle of attack protection, and speed protection. In lateral control, there is only one protection, which is for bank angle. Let's take a closer look at these protections. In a conventional aircraft, pilots must ensure that structural limitations are not exceeded. However, in the A320 family, load factor limitation is available in normal law. Load factor limitation prevents structural overstress by limiting control surface deflections through the flight control computers. Full side stick movement is always available. The structural limitations vary with configuration. In clean configuration, between plus 2.5 G to minus 1 G, flaps extended between plus 2 G to 0 G. As with the load factor limitation, if the aircraft reaches the pitch attitude protection nose up limits, then the flight control computers will override pilot demands and keep the aircraft within the safe flight limits. The pitch attitude protection limits are shown as small green dashes on the PFD. Note that the pitch up values vary depending on the aircraft configuration and speed between 30 and 20 degrees up. In the nose-down case, the computers will limit the nose-down attitude at 15 degrees. The high angle of attack protection is designed to prevent the aircraft from stalling and to ensure optimum performance in extreme maneuvers such as wind shear or GPWS warning recovery. This protection takes priority over all others. This protection displays information on the PFD speed scale. As speed decreases, it reaches VLS, lowest selectable speed with autothrust engaged. With autothrust inoperative or not engaged, the speed can reduce to the first level of angle of attack protection, V alpha protection, which is shown as the top of the amber black band, barber pole. With stick released, the flight control computers will maintain the speed at V alpha protection. If engaged, the autopilot will disconnect. Provided the autothrust is serviceable, the speed is unlikely to reduce to V alpha max before the alpha floor protection is triggered. This is indicated by an alpha floor indication on the PFD FMA and also on the engine warning display. If the pilots override V alpha protection using the side stick, the speed can reduce to V alpha max. In normal law, the flight control computers will maintain V alpha max even if a pilot holds a side stick fully aft. Nose up pitch trim is inhibited. In the protection range, the normal law demand is modified and side stick input is an angle of attack demand instead of a load factor demand. If the pilot releases the side stick at V alpha max, the speed will return to and maintain V alpha protection. The protection we will look at now is the high-speed protection. It is designed to prevent the aircraft from exceeding maximum speed. These protection limits are displayed on the PFD speed scale. VMO-MMO is shown as the bottom of the red-black barber pole. Green dashes indicate the speed at which the protection is activated. When the airspeed Mach increases above VMO-MMO, an overspeed ECAM warning is triggered, as shown in the autoflight chapter. If the airspeed Mach increases to the protection activation speed, the autopilot will disengage and the flight control computers send a pitch up command to the control surfaces to prevent further acceleration. The flight control computers will permit momentary exceedance of this speed for maneuvering if necessary. With stick released, the speed will return to VMO-MMO. Notice that the pilot cannot override the automatic pitch up. Under normal law, bank angle protection limits the angle of bank to 67 degrees, shown by green dashes on the PFD. If the pilot holds full lateral side stick, the angle of bank will increase and maintain 67 degrees. The flight director, FD, on the PFD will disappear if the angle of bank exceeds 45 degrees. If the side stick is released at any time when the bank angle exceeds 33 degrees, the aircraft will return to and maintain 33 degrees bank angle. The FD will be displayed again on the PFD when the angle of bank reduces to less than 45 degrees. Auto trim is inhibited above 33 degrees. With the angle of attack protections active, the bank angle is limited to 45 degrees and no further, if the pilot holds full lateral side stick deflection. With the high speed protection active, the system maintains a positive spiral stability to 0 degree bank angle, so that if the side stick is released, the aircraft returns to wings level. The bank angle limit is also reduced from 67 to 45 degrees. We will study the reconfiguration laws in the next module. A single failure cannot result in the loss of normal law. However, multiple failures of flight control, hydraulic or electrical systems may result in a degradation of the flight control normal law. The level of degradation will depend on the severity of the failures. Degradation of the flight control normal laws is sometimes referred to as reconfiguration. We will study these reconfiguration laws in order of increasing severity. In alternate law, ground mode is as in normal law. Flight mode, pitch control, load factor demand as in normal law. Roll control, conventional, surface deflection is proportional to side stick deflection. Roll sensitivity is proportional to airspeed. Feels more sensitive. Yaw control, turn coordination is lost. Damping available with limited authority. Landing mode, direct law when landing gear is selected down. Discussed later. Degradation to alternate law is indicated by the ECAM caution, Flight Control Alternate Law, Protection Lost. You will see this caution in detail in the Abnormal Operation module. Under alternate law, most protections are lost. Some are replaced by stabilities. We will continue by studying the loss of protections. Pitch attitude protection is lost, and the flight control computers will not limit the nose up or nose down pitch attitude. On the PFD, the green dashes, which mark the protection limits in normal law, are replaced by amber crosses. Bank angle protection is lost. On the PFD, the green dashes are replaced by amber crosses. The load factor limitation is similar to normal law. So we will go straight to the differences between normal and alternate low and high speed stability. In alternate law, the high angle of attack protection is replaced by a low speed stability. V-alpha protection and V-alpha max are replaced by a stall warning speed, VSW, indicated by a red and black barber pole. As speed approaches VSW, a gentle progressive nose-down pitch input is introduced to lower the nose and prevent further speed loss. The pitch input can be overridden by pilot input on the side stick. At VSW, an oral stall warning is triggered. The aircraft will stall if the warning is ignored. Alpha floor protection is inoperative in alternate law. In alternate law, high-speed stability replaces high-speed protection. The green dashes are replaced by amber dashes on the speed scale. Above VMO or MMO, a nose-up input is introduced to raise the nose and prevent further speed increase. This pitch tendency can be overridden by the pilots. As in normal law, if VMO-MMO is exceeded, the overspeed warning is triggered. Note that according to the failures, an alternate law without stability can exist. In this case, only the load factor limitation is provided. The high speed and low speed stabilities are lost. Stall and overspeed warnings are still operative. Direct law is the lowest level of computer flight control. Pilot inputs are now sent to the control surfaces unmodified. Because of the large number of failures required to degrade to direct law, it is unlikely to occur during normal flight. It is most likely to be encountered when the landing gear is lowered after an in-flight degradation to alternate law. In alternate law, when the landing gear is extended, the control law will degrade to direct law. You will get an ECAM warning as shown and additional messages on the PFD. We will study them later on. Direct law, as the name implies, gives a direct relationship between side stick movement and the deflections of all surfaces. In effect, the A320 behaves like a conventional aircraft, and control sensitivity will depend on airspeed. In direct law, there are no protections available, although stall and overspeed warnings will sound at the appropriate speeds. Auto trim is not available. The crew must trim the aircraft manually. Use manual pitch trim is indicated on the PFD. Auto turn coordination and Dutch roll damping are also lost. All yaw control in direct law is through the rudder pedals. In the worst case of failures, such as complete loss of flight control computer power supply, the aircraft will revert to mechanical backup mode. In this mode, the only method of control in pitch is manual adjustment of the trimmable horizontal stabilizer using the pitch trim wheel, provided either green or yellow hydraulic system is available. To indicate this, a manual pitch trim only appears in red on the PFD. Lateral control is achieved in this mode using the rudder pedals and their mechanical linkage to the rudder, provided at least one hydraulic system is available. In most cases, e.g. by resetting the flight control computer, you will be able to recover from mechanical backup to either alternate or direct law depending on the type of failure. We will now see a brief summary of the different laws and their associated protections. In normal law, all the protections are available. In alternate law, the pitch attitude protection and the bank angle protection are lost. Load factor limitation is kept. High and low speed stabilities are introduced. In alternate law without reduced protections, the high speed and the low speed stabilities are also lost. The only remaining protection is the load factor limitation. In direct law, all the protections are lost, and the aircraft handles as a conventional aircraft. In mechanical backup, no protection exists. The pitch control is performed via the pitch trim wheel and the lateral control through the rudder pedals, thanks to their mechanical linkages, provided the appropriate hydraulic systems are available. You have seen all the different laws and protections. Maybe you wonder how to recover if extreme conditions cause the aircraft to leave the protected envelope, e.g., you have been flipped over by a very severe turbulence. Here is the answer. If the limits of normal laws are exceeded, abnormal attitude laws become active. This is a safety feature to ensure that the flight control computers will never prevent the pilots recovering from an abnormal in-flight attitude. The flight control laws operate in alternate law without protections and stabilities except for load factor protection. After recovery, controls remain in alternate law without protections, but with auto trim. There is no reversion to direct law when the gear is extended. After all these emotions, you will now see the normal operation modules.